Hi, this is Kathy, your friendly TA for this course. Today we're going to solve a very interesting coding assignment called Working Hard, and together we'll explore how to determine the most optimal number of lines of code to write before taking a coffee break. Now let's get started, shall we? Here's the scenario. Chris needs to complete a programming assignment overnight. She can drink coffee to stay awake, but too much coffee makes her jittery and slows her down. The challenge is to figure out the minimum number of lines of code she needs to write before her first cup of coffee so she can finish her assignment efficiently. To solve this problem, we'll use two main approaches, a linear search and a binary search. But before we get into the searches, we need a function that calculates how many lines of code Chris can write before falling asleep. This function will use recursion. Now let's think about how we can calculate this using recursion. We'll break down the problem into smaller steps. Step 1, define the base case. The base case is the condition where the recursion stops. For our problem, the base case can be defined in several ways depending on how we analyze it. Here are a few ways to define the base case. When lines before coffee is less than 1, or when lines before coffee divided by prod loss is equal to 0. Both conditions essentially mean Chris can't write any more lines of code. You can choose the one that makes the most sense for your implementation. There are also other ways to define the base case. Step 2, define the recursive case. The recursive case is where the function calls itself with updated arguments. In our problem, after each cup of coffee, the lines of code Chris can write next is the current lines divided by the productivity loss factor. Let's illustrate this with a visual example. Imagine Chris starts with 20 lines before coffee and her productivity halves after each cup. The recursive calls will look like this. By visualizing the recursive flow, we can see how each call breaks the problem down into smaller pieces until it hits the base case, then adds up the results as it returns from each recursive call. Let's go over the steps to implement the linear search. It's important to note there are different ways to implement the linear search method. You could use lists, dictionaries, or just simple loops. Each approach has its own advantages. I'm just going for the simple loops because they're very fun. Step 1, initialize variables. We'll start by setting up variables to keep track of the lines of code written before the first cup of coffee and the number of iterations in our search. Imagine we start with 1 line and keep increasing until the total lines of code written, including the productivity drops, meet or exceed the target. And step 2, to actually perform the linear search, we'll use a loop to iterate through the possible initial lines of code, starting from 1 and moving upwards. For each iteration, we'll call the sum series function and check if the total lines written meet or exceed the target. If we find a number of initial lines that allows Chris to meet her goal, we'll stop and return that number along with the count of iterations. This way, Chris can have her coffee as soon as possible without compromising her productivity. Let's talk about how to solve this problem using binary search. Step 1, initialize variables. We start with a low initial number of lines called low and a high initial number called high, which is just above the total lines of code needed. This will set the boundaries for our binary search. In step 2, we perform the actual binary search. We use a loop to iteratively adjust the boundaries low and high based on the middle point. We calculate the total lines written using the sum series function. And if we check the total lines written are less than or greater than the target, we efficiently narrow down the range of possible initial lines. 3, determine the ideal initial lines. Once we find the exact number where the total lines written meet or exceed the target, we stop and return that number. It's important to note that binary search is effective because it halves the search space with each iteration, making it much faster than a linear search for large datasets. And that's it for today's tutorial. We've successfully implemented recursion and also linear and binary search approaches to solve the working hard problem. I hope this tutorial was helpful and gave you a better understanding of these search algorithms. If you enjoyed this video, don't forget to like and subscribe for more coding tutorials. Thanks for watching and happy coding!